Okay, so index of refraction is optical density, and when you're going in through something like air, where the index of refraction is 1, it's very easy for the electromagnetic radiation to travel through, so we find that it will speed up. Whereas something like a diamond, who has a high index of refraction being 2.42, it's difficult for light to travel through, and we see that the EMR slows down. Index of refraction has no unit, so that's something to remember. So let's look at this. A beam of red light has a wavelength of 700 nanometers and is traveling through water, which has an index of refraction of 1.33. The beam of light leaves the water and travels into a piece of flint glass with an index of refraction of 1.75. Determine the wavelength of the light when it is in the flint glass, and then compare the frequency of the incident wave to the refracted wave. So the first thing that we have to do is we have to draw a diagram, a picture. Sorry. This is the surface, and here's the line of normal. So here we have a wave come in, or a light pattern come in like this, and it's going to go like this. So this is medium number 1, and this is medium number 2. The information that we have here is that we have a wavelength of 700 nanometers, and we have an index of refraction of 1.33. Here we don't know the wavelength, but we do know the other index of refraction. Oops, but. So how do we look at it? Knowing that we're looking at index of refraction and wavelength, we know that we can have N2 over N1 is equal to lambda 1 over lambda 2. And we're going to isolate for wavelength 2. So wavelength 2 is going to be equal to lambda 1 N1 over N2. So that sees us have a value of 700 nanometers times 1.33 divided by 1.75, giving us a value of 532 nanometers. Okay, we can leave it in nanometers because it's a ratio, so we don't need to change it to meters. Compare the frequency of incident wave to the refractive wave. Well, we just read that frequency is not affected. Traveling through different mediums. Therefore, F1 would be equal to F2. Okay? A student is doing a lab and measures the speed of light to be 2.21 times 10 to the 8th meters per second as it travels through a certain substance. Use the table below to determine the identity of the substance. So this is what we're going to do. We're going to draw a diagram so that we understand what's going on. Our surface area this way and our line of normal that way. We have an angle coming in this way. And it's bending. So it's asking us to use the table below to determine the identity of the substance. This is, the index of refraction is N. So we don't know N1. It's asking us to figure it out. But we do know the velocity is 2.21 times 10 to the 8th. And here, because we're controlling it and we're looking for it being in another medium, we can set medium number 2 to be air. Okay? And so then we're looking at this relationship. N2 over N1 is equal to V1 over V2, and we're solving for N1. So it's N2 V2 over V1. Divided by into 1 times 10 to the 8th. Into, therefore, is going to equal 1.357. When we look at the chart, we see that this is the closest to 1.357. Therefore, the medium is ethanol. All right? So I'm going to leave you here to work on these questions. Do a couple. There's more to this section, and I'm going to keep going on. So here's another way of figuring out index of refraction and various parts of Snell's law. Aidan sets out to determine the speed of light in a viscous fluid by using the principles of refraction. Using a red pen laser, he manipulates the angle of incidence and records the angle of refraction. So these are incidence angles that he set up, and then he measured these angles of refraction. It's asking us to determine the sign of the angles, put it into the chart, plot the sign of the angles, determine the slope of the line, and use the slope to determine the speed of light in the viscous fluid. So the first part, when we go sine of 15 degrees, we see that we get 0.2588. 5736, 7071. And then when we do the same thing for the refractive angle, and 0.5878. Okay? Those are very simple. Just in your calculator, sine, put the angle in, and you're good to go. Plot the sign of the angles. This here is X, and this here is Y. We read a chart left to right. So this is the sine of the incident angle, and this is the sine of the refracted angle. The incident angle is in medium 2, and the refracted angle is in medium 1. So you're going to take the data from the above chart, and you're going to enter it into your calculator. And you're going to solve for y equals ax plus b. So y is your refracted angle, x is your incident angle, and a is going to be your slope. So this is going to be your refracted angle, this is going to be your incident angle, and this is going to be your slope. And when you put it through your calculator, slope is going to be equal to 0.8464, and b is going to be negative 0.01339, which means that we won't be looking at b. Now, what are we looking at in relationship? We have sine 1, sine theta 1 over sine theta 2 is equal to velocity 1 over velocity 2. And so it says that it's speed of light in a viscous fluid, but the pen light is starting from the outside. So we know that velocity 1 then is going to be 3 times 10 to the 8 meters per second. We are looking for the velocity 2, and sine theta 1 is x, sine theta 2 is y. When we solve for, when we put this in y equals mx plus b format, we need to solve for sine theta 2, because we've said that sine theta 2 is y. M is going to be the slope times sine theta 1, and then we have no b value. So when we rearrange this formula and we solve for sine theta, we see that we have V2 over V1 sine theta 1. This is when we rearrange this formula here. Well, what's in the slope position? This is going to be V2 over V1. That's what your slope is equal to. When we get this 0.8464, that's what that is. So it's okay that we don't know the second velocity. So then V2, because we need to find it, is going to be slope times velocity 1 is going to be equal to 0.8464 times 3 times 10 to the 8 meters per second. Velocity 2 is going to be 2.54 times 10 to the 8 meters per second. Okay, that's how we would solve through this one. Because of this here, slope, right here. Slope is equal to V2 over V1. So we don't need to look at sine theta or sine theta 1. We just can look at this here. We get this from the calculator and this from the known information. All right. The next one is critical angle. Actually, we're going to stop here, and I'm just going to let you work on the questions. If you want to read ahead about critical angle, that will be great. Just focus on this first part.